Welcome, everyone. I hope you had a great break. So we're back for the last 2 weeks, of course. We'll continue from the Sim to Real lecture that we left on Wednesday. To remind you, the last topic we saw, the last paper was the robot learning to solve Rubik's Cube. Our goal in this lecture is to learn policies in simulation that generalize to the real world. And indeed, that policy for orienting the cube and changing the faces of the cube was trained only in simulation. We saw about adaptive domain randomization that was introduced in that paper. How can you randomize the physics parameters of the simulator as much as you can, but no more, so that you learn a robust policy that has maximum chances of generalizing the real world. Another extremely important thing we saw for the previous paper is that every episode is not one success. The policy is an LSTM, which means it has a long memory that it can see its previous observations and actions and resulting rewards, okay, as part of the history. And that LSTM keeps trying multiple times till the end of the episode. And we saw that one episode has 50 tries, 50 successes, or an upper bound of a maximum number of steps, okay? And we saw that this long-term memory of the policy is what permits it for meta-learning to emerge. What does meta-learning mean? We saw that at test time, we go to the real robot, we bind the 2 fingers together, we put a glove and so on. The policy gets stuck, but as it tries and tries, it sees its own tries and, resulting failures because it sees the reward and actual observations, and it adapts. Eventually, it manages to orient the cube or changing the face, despite the fact that, the 2 fingers are bound together, despite the fact there's a glove on. Conditions that were never seen at training time. Is that clear? Okay, well, we have another super exciting application on real robots with policies trained solely on simulation at the end of this slide deck. But before we jump to that one, I want to discuss similar attempts of sim to real transfer of policies for driving. And the reason is that this specific paper has general principles that are actually applicable also in other domains beyond driving. Okay, it's extremely simple. It's called driving policy transfer via modularity and abstraction. Our goal is to learn to drive from pixel input all the way to low-level controls of the vehicle, okay? And guess what? If you go in simulation and you learn such a policy, you'll deploy it in the real world and things are not going to work out. And the reason, this policy cannot generalize is twofold. Number one, pixel images will look different in the real world, okay? No matter how much your artist try to make your simulator photorealistic, there will never be exact match of the visual pixels. And number two, the vehicle dynamics are different, okay? So the low-level control may be very different. Is that clear, guys? Okay, great. So these are the problems we're trying to, address. So how these people address those problems? Well, they said, instead of going all the way from pixels to low-level actions, simulation cannot help me there. But where simulation can help me is to learn a policy that goes from semantic labels to waypoints on the road where the car should go. Okay? Why you think this is the case? Why you think that this is a better idea to train this driving policy as opposed to this end-to-end pixel to low-level controls? Yes.
You can learn a different segmenter for the sim versus the real, so that way the rest of it isn't affected by that transfer.
Segmentor meaning here, image segmentor, correct? Yeah, and that is actually, interestingly, we have a big amount of annotations of images with their corresponding semantic labels in real world, okay? I mean, the computer vision field has spent a lot of money annotating images with their semantic labels, which, as you said, you can use directly in the real world. So this is good, okay? And now what about this controller? Why should we be predicting waypoints as opposed to low-level control? Yeah? Yeah, so your colleague said that there are existing controllers that can actually follow waypoints for every car. They don't need to be even learning based, right? And this is true. And the reason is that no matter what car you have, like Ferrari versus, Lada, it still needs to follow the same waypoints, despite the fact that their internal dynamics can be extremely different. Their way you need to drive them is different, okay? So this is nice because this is platform agnostic now, this policy. And then you can just plug here any controller you want to actually follow those waypoints. So by having this modular structure of, the perception module, the, labels to waypoints mapping, and then waypoints all the way to, actual controls, you're able to train something useful in simulation that can generalize in the real world. Okay, so this is what they're saying. And how they're going to evaluate that? Well, here's the thing. We have driving. There's no way we're going to take the sim policy and deploy it in the real world to see how well it drives, because this is very dangerous. So instead, what we do in this case is sim to sim. We have two different simulation environments. And here specifically, they consider two towns under two different weathers. Okay, town 1, town 2, weather 1, weather 2, and they're going to learn the model in one of those instantiations and test it in the other. And my question for you is, we have 4 combinations now of simulation environments: town 1, weather 1, town 2, weather 2, town 2, weather 1, town 1, weather 2. Where do you think is going to be the largest gap? If we train on town 1, weather 1 and test on town 2, weather 2, right? Because both the town is different and the weather is different. Is that clear? Okay, so this is going to be our test set. Let's see. Yes, so we'll evaluate them in all 4, but as we said, the different. So one of them, since we train in town 1, weather 1, if you evaluate on town 1, weather 1, you're in domain. You're in the same domain where your training data come from, right? The other 3 are out of domain. But you always need to remember that in domain, out of domain is not a binary thing. You can be a little bit out of domain, more out of domain, more out of domain. And as we said here, the weather 2, town 2 is the most out of domain, okay? That's what we said. So let's see. Let's just do exactly what we said. We just go in simulation, take semantic labels, put a CNN or some other architecture, spit out waypoints on the overhead map of where the car should go. We train that module, then we plug our perception as well as low-level controller now to test in the other environment. And as you can see, so image to control is the end-to-end module that goes all the way from pixels to low-level control, and it does really well within domain, okay? And it also does non-zero, okay, in the same weather conditions on a different town, but it really fails in the same town with different weather or the other town different weather, okay? You see, the performance of the module within domain and out of domain is dramatically different. So you always need to keep this in mind. Generalization is very important. In big parts of this course, we did not worry whatsoever about generalization. We had one environment and we're trying to discover the policy. Well, once you want to learn something in one environment and test in another environment, comes the question of generalization. So you always need to be very careful about, what test set you consider and in what dimensions these test sets are different than your training set, okay? So in any case, this purple thing, the image to control has the worst performance. And here is their proposal. And as you see, it does well within domain, but it also does reasonably well out of domain, or at least better than the end-to-end module, okay? So plus denotes models trained with data augmentation. We always do data augmentation, crops, and so on of the image input, etc. And plus DR means domain and randomization. You do whatever you want on the pixels, the input pixels, to make them look more close to not to make them, to enlarge the training distribution so that when the test environment comes, essentially you can consider it as one variation of this tremendous amount of worlds that you saw at training time. So that's it. So a very general principle here, instead of going from pixels all the way to low-level controls, you go from some intermediate perceptual input, some abstraction, to some waypoints in the world. Now, what is the downside here? There needs to be an engineer that can tell you what should be that label space. What should be that label space that you can really forget about the pixels and then just keep those labels. And this is really, really not clear. Here we just said, oh, you just need to know which is the car and what is road and what is a traffic light. And I want to ask you, can you imagine a situation in driving where such a predefined label space will actually not be enough to really drive in the world? We cannot learn an adequate policy simply by having semantic maps of where the cars are and the road and the lanes and the traffic lights and the stop signs. Yeah? You have a construction. Yeah, right, exactly. You need to know about the construction, right? Or you need to know also the driver in the stop sign, is he texting or is he looking at the sign? Self-driving car companies really have perception modules that look at the other drivers and try to figure out where those other drivers are looking at. Okay, is that clear? So basically there is this homonymous engineering loop of the humans suggesting what you need to be paying attention to, and those labels going all the way to the perception modules that take the pixels and spit out those labels from where policies can be trained. Okay, and yes, of course, all this out of domain, like construction sites or holes on the road or flying trash bags and so on. Okay. By the way, flying trash bag is an example very often given in talks, and they say, oh, look, the car presses the really abrupt brake because it doesn't recognize that it's a trash bag, while we have common sense and we know that the trash bag is not dangerous and we just move on with our car, something like this. But yes, this is all about how the sacrifices you pay once you decide to restrict your label space, okay? Now, what do humans do? Humans dramatically restrict their label space. When they give an image and I drive, I know precisely what to pay attention to and what really, really to ignore. However, I'm so effective in doing that in comparison to the machine learning model because that, let's say, label abstraction, I have learned from all my life till I enter the car, okay? Watching other drive, knowing that trash box is nothing, is kind of soft, I'm not scared of it, and so on, knowing that humans are not supposed to be driven close to and slowing down on construction, etc. So humans and in general, we're so intelligent and we learn fast because we transfer tremendous amount of knowledge from environment to environment. And this is also what we said when we talked about Atari games, right? That we come and we have humongous amounts of priors about what's a cave, what's a monster, what's a key, that we can use, okay, ready out of the box, while the machine learning model does not have those priors. Is that clear? Same with driving, okay? So we know what texting is, and somebody who texts cannot see before, even if this has nothing ever happened to us in our driving history. Is that clear? Okay. All right. So here is another success story of learning in simulation. Okay. Rapid motor adaptation, or RMA. This is a very interesting paper and has also follow-ups with visual input that I will talk to you in case you want to read it. It's very interesting, both because the results are very impressive. Let's see. So here is a little robot. That robot doesn't have a camera, so it doesn't have any perception. It's actually blind. But as you see, he can move around rocks and so on. And now it's going to go down the stairs. Okay, and now the question for those that were in the talk of Boston Dynamics would be, we saw similar behaviors with Boston Dynamic robots, and the speaker was explicit saying that there was no machine learning used in actually all those behaviors of the robots, and those that did not see the talk actually can go online and see what amazing things the robots from Boston Dynamics can do. And why I find this work exciting is that now we can learn, first of all, the robots in Boston Dynamics were much taller, so you don't need to learn dynamic behaviors where actually both like multiple feet are off the ground, like more dynamic behaviors. And second, everything was engineered, okay? While here, all those diverse behaviors of walking around in all these diverse and difficult terrains actually are all learned, okay? Now, there is a big engineering effort on building the simulator for that particular robot. But that engineering effort is done once, and then you train your robot there, and then you deploy it in the real world. All right. So now we'll discuss a learning-based solution, and specifically reinforcement learning-based solution for this problem. Do you have any questions? Okay, so then I have a question for you. How would you do it based on domain randomization that we discussed earlier in this lecture on Wednesday? If I give you the robot model for that robot in simulation and a lot of different environments, what would be the domain randomization way of training a walking policy? Yeah, take your time, but I expect somebody is going to raise his hand or her hand and say something. Let's say I give you a simulator and I tell you I want you to train a robot that can walk forward. How would you do it based on the things that we know in the course? Yes?
Pick an environment and change the hyperparameters, increase the threshold, see if the robot can adapt to it. If not, we discard it.
Great. And how would you train your RL policy? Which one would you use and how would you design your reward, let's say?
I think it's called BCQ or something, but I don't remember for sure.
Why would you use BCQ?
To restrict my action space to the ones which I have already explored.
Why you need to do that? Okay, so your colleague says that he's going to go in the simulation environment and, well, there wouldn't be some reward function, which we'll discuss what should be because the robot needs to move forward, and that he's going to use batch constraint Q learning to learn to walk. Any other suggestions? Yes?
PPO, and our reward is just distance from starting location.
Okay, so your colleague says that we don't need batch constraint Q learning. This is not offline RL, it's just standard online RL in simulation. So I'm just going to use any model-free method, for example, PPO, and the reward will be distance traversed, or maybe velocity of the robot and so on. That's correct. So they also used some extra reward function to minimize energy consumption. But that's pretty much right. Yes, that's a standard reward. And the cool thing about this reward for locomotion is what? It's not sparse in time. And that's why learning to walk is actually not the hardest problem that can be out there, precisely because rewards are not sparse. And we know that reinforcement learning, like exactly what your colleague suggested, just PPO actually can work in that case. Now, I want to ask you, imagine, so this is the standard thing we would do. We just take a model free RL, put a reward function, go in a simulation environment. Now, we want to also make sure that we're going to jump the sim to real gap. So what are we going to do in addition to what your colleague suggested? Yes?
Vary the environment pretty greatly, having like flat surfaces.
Yes, exactly. And your first colleague also mentioned precisely that. So now your colleagues are saying, we're also going to change the physics parameters of those environments. Let me show you how those environments are going to look like, which is super. So they're going to learn one policy to work in all those environments, right? Sorry if the video breaks. And you're saying, okay, this is not surprising. I know from my domain randomization that, again, I'm going to learn one policy across all physics variations. Okay, so what's the new thing here, right? Isn't this a baseline, just domain randomization? Yes, of course, it's going to be a baseline. Now we'll discuss a method that actually does better than that baseline, okay? Okay, so the goal is I want to go to unseen environments and still do well, of course. Yes, clearly unseen because I'm going to train in simulation and I'm going to deploy in the real world, right? So clearly they're going to be unseen. So here is the amazing thing. You're going to train the robot on things like that. It's pretty crazy. Now, the good thing is that this robot is blind, so you don't need to worry about visuals, okay? You only need to worry about, friction on the ground and how smooth the ground is and so on. But, the whole world can be black and white. There's no camera here, okay? It's only the feedback that the robot gets through his sensors. Is that clear? Okay. Does this make sense? So you're going to be varying those environments. So I'll show you in which way you're going to vary them. Here are some physics parameters: mass, center of mass, friction, terrain height, and motor strength. And this is precisely what you will be varying during your what you call domain randomization. You're going to be just changing those guides. And the height, terrain height, essentially you're going to make those, little pyramids higher or lower. Okay, so you'll make the terrain rougher or smoother. Is that clear? Okay. Now, and the base policy will be a standard LSTM, okay, that takes as input. So let's see. So actually, this is the baseline. This is the baseline. Somebody here is changing the environments, and there is one policy that takes as input the current configuration of the robot and potentially a history of the previous actions. And that's the LSTM policy that we saw, for example, in the OpenAI Rubik's Cube robot, right? And it's just going to predict the action, what the robot should do next. Okay? Now, what is the new thing here? Because so far is the same as in our previous paper. The new thing is that these environment parameters, okay, will be embedded through an MLP, through a linear layer or non-linear layer into some embedding vector Z. Okay, a pretty small embedding vector. And this embedding vector also is going to be fed into the policy. This is the big change. Okay, so the physics parameters do not change and the policy is agnostic to them. You don't try to build a policy that is robust across all environment variations, which means what this means robust. It's the same policy that you deploy, nothing changes across all environments. Instead, it's as if you know the variation of the environments and you feed them into an encoder and you get a vector and that vector informs the policy. So in this way, the policy can directly adapt in principle to the environment. As the Z changes, the policy will change. Okay. Now, do you have any questions on this? Yes.
That would be unknown in the real world, right?
Excellent. Now your colleague is saying, okay, but who's going to give me those numbers? These are unknown in the real world, correct? Excellent question. And there's going to be something which we call adaptation module, which will take as input the past history of the robot, okay, to predict this Z embedding vector. And this is precisely what we're going to see now in detail. But any other questions on the difference between this policy and the previous policy that we're trying with domain randomization? Okay, so here is the robot trying to walk in simulation. Okay, so the reward is exactly what you said, moving faster, but also minimizing ground impact. So you want to be soft, so the robot to walk in a soft way. All right, so imagine for now we're training. And because we are training and we make the world, the simulation world, we are gods. So we have those numbers. Do you guys agree? We have those numbers. So we can train the policy with reinforcement learning, with PPO, exactly what your colleague said. Do you all agree? Okay. Great. So what happens now is how can we deploy it? Those red are unknown. Okay, this is unknown. Is exactly what your colleague pointed out. So these are unavailable. So what are we going to do? Well, at training time, we will learn to estimate those guys. And how we're going to estimate them? Well, we're going to give an adaptation module. And this adaptation module will have access to a very long history, 50 steps. I mean, it's not that long. And based on how did the robot move, like, for example, I was sliding a lot, okay? And I can see that. I can measure how much progress I made by looking at my the arrangements of my joints. So based on, by the way, I'm blind, and by feeling how I move for 50 steps, I should be able to predict the Z, the embedding vector, okay? Now the question is, how you're going to train this adaptation module? How you're going to train this adaptation module? Does anybody want to tell us how we're going to train this adaptation module? Yes? With supervised learning. Exactly. There's no RL here. It's supervised learning. It's just a regression of the Z. The regression of the Z. Okay? Exactly. Perfect. And once you train it, at test time, of course, it's frozen. Okay, the weights are frozen. And the only job of that adaptation module is to be predicting the environment embedding vector to be fed into our policy. Okay? Okay. And my question for you is the following. There are two things here, right? There is some bunch of numbers here and a small embedding vector there. Why we should not be predicting those numbers as opposed to the embedding vector? This is the question. Actually, by the way, just to put you in context, a lot of work in robotics is called like system identification, and their job is to predict each and every value of the different physics parameters of your environment. Okay? Here, we're not going to be predicting those explicit physics parameters. We're going to be predicting the environment embedding vector Z. Okay? Yes?
If you try to predict all of those, it just makes your job a lot harder because you don't really care about those actual values. You care about how those values affect your robot. And by definition, it's easier to, from what your robot's behavior, it's easier to figure out that embedding that vector because that's how it directly affects your robot. Yes.
Your colleague said that if you try to predict those earlier numbers, you're doing a harder task. The only thing you care is how those numbers affect your policy, correct? Another thing I want to mention is, like if you ask me, for example, to predict those guys in this explicit fashion, maybe it's just an impossible. Maybe it's, as we say, unidentifiable. Maybe two values of those can be changed. And you know what? My past 50-step history is exactly the same. Does this make sense? So it can be that multiple configuration of these guys may be mapping exactly to the same embedding vector. Okay? So if you try to predict these guys, is a much harder problem than predicting the succinct summary embedding vector. Is that clear? Okay. So let's put then these two things together. Okay, let's put these two things together. So here is how it happens. Oop. Regress. So, okay, you cannot see the regress. But here is the policy. At training time, you just do two things. In the first phase, you just train with reinforcement learning. Okay? And at the second phase, you just train the adaptation module with regression. Just supervised learning. Okay? That's it. And the base policy stays the same. Okay? You just freeze the base policy. Is that clear? Yeah?
For training the adaptation module, do we only use some of the training data? Like, how do we make sure that we don't use data from, because the environmental factor code is going to be changing as we train, right? So Z will be changing as we train. So like, do we only take some of that like N data whenever we train
No, I think so. First, you need this needs to converge first of all, and once this converges, then you run it. Then you collect the 50 past trajectories, and you pass them, and you get the z, and that z is the same that these guys give you, right? So this gives you the ground truth. This guy gives you the ground truth, and this is also frozen. And then this provides ground truth for your adaptation module. In the second phase, only the adaptation module is trained.
Okay, so we recollect the data for the.
Yeah. Yes. Yes, because these guys change, right? Your history changes as your RL policy changes. Yes, please.
So here, I'm confused by these actions. So if I try to take an action and my action failed, then let's say I slipped, then that information would be useful to predict these parameters.
Yes.
But is this action A just what I thought I took the action, or what actually happened?
Yeah, very good. So what you think that you did, you say, now I'm going to step forward and I'm going to move my joints in this way, and I expect to go forwards. By the way, there's no expectation here. This robot doesn't have a forward model, okay? But then instead of moving forward, I actually slipped and stayed in the same state. So the fact that I stayed in the same place is actually observable here on the X because it's a state. So the robot can figure out how much it has moved. In the same way I can figure out that I moved. Do you see? Okay. So you're like, look, I'm trying to move, but I stay in the same place. So the robot knows that because it has access to its own actions and to its states. Okay. Great. All right. That's it. Now, so this is an oily surface, and now the robot is going to come and it's going to walk. Okay. And in the beginning, you see that it is getting stuck in the beginning, but then the adaptation module kicks in, and then it is able to adapt and move forward. Okay. Do you see the adaptation? Okay. All right. Okay. So basically here it shows the prediction of those z values. I think the z vector is 5 values long. And as you see over time, they predicted better. Yeah. Okay. So you're walking, and the only thing that's changing is your z values. Of course, your policy can still be predicting actions of what to do. Yes. So here is the interesting comparison that you should find in the paper. Robust is the domain randomization baseline. And as you see, it does worse than RMA, than the adaptation. Okay. It's a very good baseline. It's actually the best out there, but it does much worse than the adaptive policy. Expert is a policy that has access to the true environment factors. Okay. Of course, it does better, but not by much. So this shows that the adaptation module is indeed pretty effective in predicting the environment embedding. RMA without adaptation is just you deploy the base policy. I mean, of course, it's going to be worse than the robust because it was not trained to do well for a constant Z on crazy environments. Okay. It was trained to do well with the appropriate Z. Okay. So I think these are very good comparisons that you should check. That you should check. Now, the sysid is trying to do identification of the environment parameters, not of the embedding vector, but before the embedding, this thing that we just discussed. Okay. Okay. So this is what I wanted to discuss. This is our last work in a Sim to Real lecture. So please let me know if you have any questions, and I will move to our next lectures here. Okay. Do you have any questions? Okay, great. So now we're going to discuss about visual imitation, okay, and learning by observation. So it's going to take both today, our 45 minutes, and a little bit of Wednesday, okay. What is visual imitation? Well, you remember when we discussed about imitation learning, we said there are two imitations. There is a biologically plausible imitation, which is you imitate by watching. And there is the non-biologically plausible imitation that we currently do, which is kinesthetic imitation, where you clone actions, okay? Because the actions are readily available to you. What is the kinesthetic imitation? It means somebody takes over your end effectors and moves them around, so you know exactly what to do. One very convenient scenario for kinesthetic imitation is driving cars, because you have the driving log. The driving log has exactly the actions that actually the car took. But we said what humans do is they watch and they can adapt and map the actions of the teacher to their action space, okay? And the teacher can be a very strong, big man, and you can be a tiny little baby, and still you're going to try to imitate something with your two hands, with your little fingers, and so on, okay? So very critical for the success of visual imitation is, of course, machine perception, right? You need to be able to visually detect what's happening in the world, okay? To see if you're imitating correctly the teacher, okay? And you will see that as computer vision makes progress, visual imitation also makes progress. And today we'll discuss few examples of this, all right? Okay, great. So you want to do something like that. You want to have a human that demonstrates you a task, okay? And you want to have the robot to go and imitate it. That's what you want to do. And the better you can understand the environment, the better, of course, you can imitate. Okay, you need to perceive the world state. You need to figure out where the objects are, how the objects change, and so on. Yes. All right. So I received a question by a student about the problem of predicting sub-goals and imitating the sub-goals. You remember we said that when discussed about iris, learning from large-scale demonstration data. So this thing of breaking the task into prediction of waypoints and then hitting every waypoint is gaining popularity. We just saw it also for driving, right? So the job of the policy was to predict the waypoint, and we had the low-level controller take us from waypoint to waypoint, just like a few slides ago. And here is another general way of this, okay? And I want you to pay attention. I think it's a very general theme. And the theme is the following. I watch videos, and I also act in the world, and I want to make sure that the visuals that I generate, the world states that I generate, match in embedding distance the visuals of the teacher. That's all. So basically, there is a very dense per time step reward by matching visual features, okay? And the person or researcher that does the better visual matching wins, okay? The person that has the best visual representation wins because this is going to be able to generate the most, let's say, accurate rewards, the rewards that can generalize across most environments, and I will do well. Now, unfortunately, this is a super ridiculous example of environment change. Now, I'll show you what I mean. So some people play video games, and then they put those video games in YouTube for some reason. And now what we're going to do is we're going to use those uploaded video games to guide us of how to play a video game, okay? And this is kind of ridiculous domain gap, because you're going to be playing, let's say, Tetris, and I will also be playing Tetris or Montezuma's Revenge and so on. And the visuals are not going to be that diverse. Now I'm going to show you how they look. So maybe in your visuals, you have more light green, and this one reaches lower. And in my screen, it reaches higher, and is actually not that green. And in the other person's screen, it's going to have this guy extra here. And in the other person's screen, it's going to have this other extra thing there. And I need to learn a visual representation that can match across two different domains. This is what I'll be watching. This is my execution space. And as I move around and I, do good things like going down ladders and so on, I need to be matching my visual observations to the observations of the teacher. Is that clear? Now, the good thing is that there's no human hand. That's great. And so on. But you can get the general idea, which is I want to learn an encoder and neural weights that will take my frame and their frame. And when they do inner product of their encoding vectors, that inner product will be high when we're in the same state and lower when we are in different states. That's the idea. Okay? Is that clear? Now, the question is how we're going to learn that visual similarity. Now, somebody can say, don't worry about encoding. Just take those images and take an L2 distance on the pixel space with the images of the imitator, right? And when the L2 distance is lower, it means that you are closer to that particular configuration. Do you guys see problems with this approach? Okay, what are the problems? Of just measuring, monitoring progress based on L2 pixel distance between your observations and the teacher's observations. Yes.
If the frame is off by a little bit, then like the distance will be large, like maybe the teacher will be just like off by a little bit.
Yeah, exactly. Your colleague is saying even a tiny little shift. Imagine there are identical states. There is a tiny little shift. There's a tiny little lightning change. Is going to cause a very large L2 pixel distance. Okay, much larger than if they're maybe completely different states, but the background color is the same. So he says L2 pixel distances are not semantically meaningful. They cannot really tell me when I'm making good progress into hitting your trajectory. Okay. Does this make sense? So excellent point. Excellent point. So now the question is, we need to find some general feature distance. And given your background, guys, what do you think we should do about that? So L2 pixel distance is a baseline that I proposed. And we said, okay, this is a very bad baseline. What would be a slightly better baseline? But by the way, just before we describe how we're going to compute that feature distance, I just want to tell you how the imitation will happen. I will have a single trajectory. This is a single demonstration trajectory, okay, from a teacher, and I will imitate it, and I will be doing, my exploration and so on. And whenever I see an observation that actually matches and has high score with the corresponding image of the teacher, then I will give reward to myself. I'll reward myself. So essentially, because I will have such a good visual encoder, I will be able to know where I am in the demonstration of the teacher. Like, for example, now I went down the staircase. Now I was able to jump over the cliff and so on. Do you see? And the rewards are going to be based on how well I traverse the demonstration of the teacher. Is that clear? And I will be imitating one demonstration at a time. Do you see? So actions don't matter here. I will do in RL to estimate actions. The only thing I use from the teacher is the visual observations. And indeed, when somebody uploads their video game on YouTube, you don't know what joystick actions they did. You only see the frames, right? So I will use visual imitation. I will just use the observations to actually play the game. This might remind you of another word we saw about, because this is also the Montezuma revenge environment, is learning to play Montezuma's revenge from a single demonstration. You remember that one? Do you remember the difference between that work and this work? Mm-hmm.
You have the kinesthetic information, not just the visual, but the ground truth state, the actions, everything.
We had the state and actions, and we have rewards. Well, we
don't have the actions.
Here we don't have the actions at all. That's true.
The visions is slightly distorted based on whatever streamer set up here.
Mm-hmm. Okay, but let me ask you, in that paper, did we use the actions of the teacher? Did we use them?
Didn't we use them to reset?
We were using the state to reset. To reset, you just need the state. Yes, you're saying we were running those in the deterministic part.
Yeah.
Yes, so you would have the state of the simulator and we can wake up in that particular state, yes. But other than that, we wouldn't imitate the actions, right? We didn't have any cloning objective there, you remember?
Yeah.
Okay, great, exactly. So we're just resetting. So here there's no resetting. You just start from the beginning. And also we didn't use any visuals from the teacher, right? Okay, we just use the input images and then spit out actions. That was our policy. Well, here we're going to be looking at the visuals of the teacher and our visuals and be supplying to ourselves rewards, okay, in a standard model free RL method. Is that clear? Okay. Yes. I mean, deterministic in what sense? I think, let me explain. So I think in all those video games, different monsters may come in and out, but you still need to do the same things. You still need to jump there and to grab a particular key and then go to the cave. And I don't think these things move. Now, you may need to do different extra actions. Maybe new monsters show up and you need to kill it, but you can do that here. So it doesn't restrict you on what actions you need to do to hit the next visual, okay? You can deviate, but as soon as you reach in a stable state and you're like, oh yeah, I jumped over the skull and yes, now I'm in this, I progressed over where I was in my demonstration trajectory, you will be rewarded, okay? And how do you know that you're progressing over the demonstration trajectory? You just compute inner product between your image encoding and the image encoding from the teacher, okay?
Confusion is if there's like multiple monsters that weren't there in the demonstration, isn't that inner product getting larger as a result of something that you're not doing? Right, like a new monster shows up, that kind of increases this distance, even though you haven't actually made it.
Right, but actually you are tracking it, so you know you're here. You know you're in a particular place, and now you know that you need to find the next state in demonstration trajectories that you're close to. So you just play around till you reach to the state, all right? So you cannot go backwards because you won't be rewarded. There is a temporal structure here, and these are the past collected rewards, and these are the active rewards. You will only be rewarded if you reach those guys, and these are in the future. So you have a temporal idea, a very detailed progress monitoring of where you are in the trajectory of the teacher. Does this make sense? Okay, great. This is, by the way, very, very general idea, guys. There is a teacher. We're going to see it later with a different image matching function, okay? Here, the image matching function is take an image, make 1D vector, take the image of the teacher, make 1D vector, compute an inner product, and this is your matching score. And that's fine. This is a very legit way of measuring similarity, very unstructured. It doesn't consider what objects are in this image and what objects are in that image and so on, but it is a baseline, okay? We will see something more detailed later in the lecture. Now, my question is the following. So we're kind of aware now how we're going to imitate some very dumb, just move forward and try to match the images of the teacher. And now the question is how we're going to train the encoder weights. This is the important question. How we're going to come up with this magic matching function that will tell you, yes, when two states from Montezuma events are the same, and no when they're not the same, in a semantic way. It will not worry about if the staircase is green or red. It will not worry if there is this extra guy hanging around on the frame, as you saw earlier. Okay, it will only worry, are the objects in the right place or not? Do you see? So this means semantic similarity. Now, okay, so now the question is how we're going to do that. Does anybody know a baseline to suggest? I mean, anything better than matching pixels is welcome now for you to suggest. Yes.
You can use an autoencoder. Use a latent vector of the auto.
Very nice. So your colleague says, let's train for image reconstruction and get the latent embedding, and probably it's going to do better. That's right. I do believe also that it's going to do better. Okay. I also believe that. And indeed, the earliest methods for representation learning were all driven by autoencoding, okay? What is a more recent, but by the way, whatever we're discussing now is the central topic of representation learning or self-supervised representation learning. Why self-supervised? Because what are the annotations that are missing? I have access to tons of Montezuma Revenge solution videos, but I do not have the supervision of which image matches with which image. Is that clear? I don't have the alignment, the temporal alignment between those videos. I don't know that, oh yeah, he's in the tunnel and he's entering also the tunnel, and here also he's entering the tunnel and so on, and then all these frames are in exactly the same spot of our agent entering the tunnel. I don't have this alignment information. So I'm unsupervised. I need to come up with an unsupervised way to learn features that if I use those features across my different demo videos, as well as the video of my agent, I'll be able to come up with this alignment. We're trying to align now our agent to a teacher, and we can use the same encoding function to align two different teacher videos, correct? Yes. Yeah, so now your colleague says, what if we do some next frame prediction? And the most fancy way to do next frame prediction, well, okay, that sounds a bit difficult. I see. A bit difficult because we don't have access to actions, and this next frame prediction may be, I mean, we'll do some contrastive next frame prediction. We'll condition a bunch of frames and predict the representation for the next frame. And we believe that this encoder that is trained to contrastively predict the future will actually learn good representations, and I can use them, to do inner product and infer alignment. I think this is what you're saying. Yes, that's one solution. What is another method that for static images, it has worked really well? We'll see details in the next lecture. It's extremely, extremely naive. And it was proposed 1980s, okay? You take an image and you change it a little bit, and then you featureize the original image and the augmented one, and you ask for the representations to be close, and the representation of this image and other images to be far. This is called instance discrimination task, and it has worked really well on, single image representation learning. We'll see this coming. Wednesday. We'll see this on Wednesday. Now, for videos, what people do, which is a little bit easier than what your colleague suggested, is you take two frames and you try to predict how far away they are. You try to predict their distance. Okay, this is the method that they suggested. Now, there are many other methods. For example, you can look up temporal contrastive networks. It's again another robot paper that wants to learn from visual imitation and needs to do some feature learning and uses some temporal contrastive pretext task that says, okay, frames that are nearby put their feature representation close, and features that are frames that are far away put their feature representations far away in embedding space. This is not what happens in our paper. In our paper happens this very simple task. You take a frame, you encode it, and you map it through some CNN to a 1D vector, and then you do that for two frames, W, like this frame and that frame, and you map it to these two red vectors. And then you consider these two red vectors and you try to predict, using a classification task, in which distance do they reside? Are they 0 frames apart, 1 frame apart, 2, 3 to 4, and so on? So you have some beans of the temporal distance, and you train weights of your encoder, whatever you see here in green, to optimize for this classification task. And my question for you is the following. Do we have the labels for this classification task? We have. So what here happens in representation learning? You have a very difficult problem, which is what? Cross-video alignment, for which you don't have the supervision. And what do you do instead? You come up with a pretext task, something that looks super naive. Take two frames, predict how far away they are, for which you do have labels, and then you train your network to predict the labels for that pretext task. And people have proposed gazillion set of pretext tasks. For example, you take an image, you rotate it, you take the two image and the rotate once, and you need to predict the rotation. That's one way. That's another task. Okay. Here we're in videos, so we need to focus ourselves on tasks that are pretext tasks that make sense for videos. And here is one, right? Do you remember when we talked about intelligent exploration, when we talked about memory through reachability, there was a pretext task to train the comparative network. Does anybody remember that pretext task? Which, by the way, is going to enter in quiz 3 as well. Does anybody remember the paper, Exploration Through Reachability, where we were using a non-parametric memory, and when we reach a new observation, our agent had to do to reason about, is this observation something that I have seen before or it's a new one? And guess what? We didn't have supervision for those labels, okay? So what did we do to train this comparative network that would take 2 frames, the current observation in memory, and decide, yes, this is close or this is far? Yeah? So we would consider trajectories of our agent, and we wouldn't be predicting exact distance like here or binning distance, but we would just say, oh, here is the frame. And whatever is nearby to me, it's close. I call those close frames, and what is far away is far. And that just I train my feature embedding to say these are close and these are far. This is exactly the temporal contrastive task that I just talked about. Okay. Here is a little bit different. Here's a little bit different. You embed 2 frames and you want to predict their temporal distance. Now, I don't think we should fight which pretext task is the best, but in any case, we need to know about those. Okay. Okay. Now I want to ask you something. As you see, these 2 frames will always be coming from the same video. Now, upon training of your encoder, you will need to use it to compare frames from different videos. Do you see? Same as in that memory through reachability. You would train the comparative network for frames within the same trajectory of your agent, and then you would use it to compare one image in your memory and the current observation of the agent, which are not on the same video. Do you see? So this is the idea of pretext task. The pretext task is an easy task where you train your features to use them in a difficult task. Is that clear? Do you have any questions here? So we'll see those self-supervised visual representation also on Wednesday. I want to tell you about another very, very interesting pretext task. Very interesting. And the reason it's very interesting because it uses 2 modalities, audio and visual frames. Now, when you play video games, there is very interesting audio effects, right? Like all video games have some very weird music, and then you have visual indications when you jump and when you kill a monster. So these are very, very useful to train visual representations. And here is the second thing we're going to do. We'll take the audio channel, do you see? And we will feed it into another network, Psi. Of course, this network has different weights and different architecture data. This is different input, okay? This also is going to be mapped into 1D vector. And what I'm going to do now, I'm going to have very similar pretext task, but instead of feeding 2 video frames, I'm going to be feeding 1 visual and 1 audio. And I should be able to be predicting, is this audio and visual, how far away they are in time? Is that clear? Are they 0 frames apart? Are they 1? Are they far away? And so on. Okay? So I want to tell you that this is very, very common to learn visual representations in videos using audio. The most common pretext task that you'll see is the more plain contrastive version of that, which means, put the audio features and the visual features that come from the same frame close. Put the visual features and audio features that come from far away frames far. Is that clear? Okay. So you will do both of them. You'll use both of those to train, which I think is very, very interesting. And now, what are we going to do with the Psi at test time? What are we going to do with the Psi? We're going to throw it away. That's what we're going to do. We use the Psi encoding of the audio features only to train the visual encoder. Okay, so at test time, when I imitate, I don't worry about the audio, I use only the visual. Now, if you think that at test time you also want to use the audio, that's fine. Then you need to take a, encoding of your observation. The observation should be both audio and visual, and encode them, make 1 vector and do inner product. Okay. Okay, so this is what it is. And as you see, of course, if you don't have a single demonstration to imitate, you do really, really, really bad. And we explained in the Go Explore lecture why you do so bad, because you need on average 1 million interactions just to get one non-zero reward. So it's super hopeless. But once I give you one imitation, the rewards are much closer to you, so you do much better. Is that clear? Okay. Great. Do you have any questions? Big questions on self-supervised learning, because we'll see more details on Wednesday. We'll see more self-supervised tasks. We'll see about augmentations. We'll see a lot of gazillion ways to train your visual encoders to be useful for reinforcement learning, visual reinforcement learning directly from image pixels. Do you have any questions? Okay, so now we'll see something very, very intuitive. So we said, as computer vision does progress, visual imitation also progresses. So what you see here is YouTube videos where people are doing acrobatics, and in the bottom, you see an agent in a physics-aware simulator imitating those actions, okay? Now, based on what we discussed, how do you think we should go about solving this problem? Who would like to? Because the right previous paper, right, solving difficult exploration games by watching YouTube, suggested one way where I give you a video and you imitate it, correct? So what would be, how would you adapt that methodology to actually imitate those complicated actions? Who would like to tell us something? Yes.
The difference is that this environment is going to look very different from the environment in the videos. So
you're saying the environment of the agent, which is here, this guy, is going to look visually very different than the imitation images. Is this what you're saying? Very good observation. Did you see the observation of your colleague? So he said in the previous example, the uploaded YouTube video of Montezuma's Revenge and the images of Montezuma that my agent would get are pretty similar. We saw that. While here, they can be pretty different. Is this what you're saying? Excellent point. Excellent point. Okay, that is true. But if you say, I don't care, my visual encoder will handle that, then what would you do? The same thing. So you would take the videos, right? And you would take different frames, you'd encode them. You would predict how close or far are they in time, right? With this binning process, correct? I don't know if there is audio here. Maybe there is some audio. Sometimes in the karate, there is some sound effects that humans make some noise when they do things. But you could do also that, correct? And then you would encode this guy and you'd encode that guy, and you hope that the future encoder will tell you where you are in the activity and will guide you during your model-free RL. Do you guys agree with this plan? And if you don't agree, you can ask a question and say, look, this is not clear. That is totally fine. What do you think about this plan? Do you think it's going to work?
problem might be that it's harder to segment into past and current future actions, because once you start the action, you might not be able to, like, it might be harder to learn from a single trajectory, I guess, because you have to do it exactly the sequence of actions. You can't sort of switch.
Okay, so your colleague is saying it's hard to learn by imitating one trajectory. This is what we did in the previous paper. He says if you imitate from one trajectory, you don't mix and match. And guess what? This algorithm that you see here, these results imitated a single trajectory at a time. So this is not the answer, okay? Now, my question for you guys is, what do you think about the plan that your colleague said? We're just going to learn a visual encoder like the previous paper and use it as inner product to give us rewards, imitation rewards of how well we're moving along the trajectory. Okay? Yes.
It's hard because here it doesn't seem like it has discrete unlimited actions. Like discovering this, trying to do something and making it achieve the exact same thing that happened in the video sounds tough here.
So your colleague is saying in Montezuma's revenge, the actions are discrete, while here are continuous. And this makes things different because of this. That is true. The action space here is continuous and there is discrete. That's true. That's true. But this is not the main difference because still we're going to do model free RL with continuous actions. Okay. Yeah. Why we think that anybody else? Yes.
I was just gonna ask if there's issues with like identifiability of like factors, where like some of these videos were doing kind of like a profile view, so you may have issues with like identifying like a back arm from like someone's body, whereas in like the previous one, you're able to like, kind of like perfectly observe.
So now your colleague saying something else. Now he's saying the video has a 3D world, while before it was a 2D world, kind of, in the Montezuma's revenge. Is this what you're saying? Yeah, excellent. Yeah, now we have a 3D world, and then we had the 2D world. That's true. And, okay. But I can say, oh, my feature encoder is awesome, and it's going to figure it out. When the agent has his hands up, they're going to be up, and then when they are lower, going to be lower. Yeah, I think, yes. Do you want to say something or no?
The gas, like the robot is going to be different than like the human, so then
yeah,
maybe it's hard. Like there's gonna be some like difference, even though like the robot is like doing those actions really well. Like there's still some difference.
Very nice. So your colleague is saying the following: even if this guy manages to do the backflip, this is also exactly what your first colleague said. Even if it manages to do it, my visual encoder won't be able to match. It just won't work. That's what your colleague is saying. Because even if I do my pretest tasks, and the pretest tasks here take frames from here, pairs of frames, and they take pairs of frames from there, and you know what? I can generate some random trajectories with my agent doing crazy things and feeding them in my encoder and predicting time. Are these close? Are they different? There is no way that visual encoder will be able to match these two extremely different worlds. That's what your colleague is saying. He says it's a computer vision problem. This visual encoder that is self-supervised is just not going to work, correct? However, me and you can totally, map those key points of the body to those key points of the body. Why? Because we're so familiar with bodies, and human bodies and animal bodies and bodies in general, okay? And this is precisely the only difference, guys. The only difference is the visual encoding. Instead of using this vanilla self-supervised feature encoder that we saw earlier, we're going to use a insanely supervised encoder that takes images and maps them to key points, body joints. Not only we're going to map them to body joints in 2D, where your 2D key points are, but we're going to match them in 3D. What your colleague point out that the world is 3D. And we're going to do this insane, let's say, estimation, computer vision estimation of the 3D human pose over time. And then my matching and reward function will not be based on generic single frame image like vector, but it will be based on the key points. And I will manually know because I know my agent and I know where is his neck and his shoulder. So as the agents move around in the environment, I know precisely where his joints are. So I will make sure that the translation of his left knee is precisely at the location of the left knee of the person in the video. So I will just basically capitalize over computer vision technologies to take these videos and map them into 3D reconstructed motions, okay, where precisely I know the 3D key points of the human body here, and then I will do this matching, and that's how I'm going to get the reward. And all the rest stay the same. I'm still going to have a model free RL, and everything is going to be exactly the same, and I will be able to learn from passive videos, and I will not need to do any actions, and I will use simulation, and my reward is going to be dense, and so on. And it's okay that my actions are continuous, and it's okay that my video is 3D. So let's see. So here, this is just computer vision. And I can explain you, I can give you details of how do you go from that video into that 3D reconstructed motion. And here is a backflip also. And by the way, this is just a mesh. This is just a 3D mesh. There is no physics. There's no physics. So if you try to make the agent follow precisely those locations, probably you're not going to be able to do it. First of all, because the lengths of the arms are not the same as the agent, but also the agent is probably going to fall. So you can use it as a guidance to the agent, okay? Because the agent needs to handle gravity, okay? And maybe needs to flip a bit faster, right? In the same way that you guys, when you do backflips, whether you do it in this terrain versus another terrain, you adapt a little bit, okay? So just to be clear, this is just a guidance. This is just a 3D mesh in space and time. A 3D mesh is just a bunch of nodes, like thousands of nodes of the human body that move over time. So here is what it is. So now we'll discuss a little bit how do we go from a 2D video into a 3D human mesh model, okay? Is that clear? Okay, now this is a big technology. In fact, the whole startup was made out of this. The people that built those models made a startup which they sold. And how did they do that? Well, they had a very expensive scanner. They brought many people, they scanned them up, and then they aligned their scans. And because everybody was scanned like this, the alignment process was easier. What is the alignment process? You take the node here of my arm and you find the corresponding node on someone else's arm. Okay, and because we're both in the same pose, you are able to do this mapping. And essentially what these people give to the community is this amazing model they call CMPL, which is simple. They call it simple, which does the following thing. It is controlled by two sets of parameters, the pose and the shape. And as you vary the pose, so this is the shape. So here's you varying beta, and here is you varying theta. So the theta controls the pose of the mesh, and the shape controls the thickness or how thin it is. And the interesting thing is that this is a differentiable mapping, which is what? Here is few parameters, let's say 13 in total, and they're mapped through a differential way, through some function, to 30,000 locations to 3D locations of 30,000 vertices of the mesh model. Okay, so these people in their paper show how you can compute a low parametric model that with those few parameters you can control that huge mesh. And now the idea is the following: I give you an image, so the estimation problem is you need to give me those parameters. So instead of searching over 30,000 numbers of where all these mesh locations are, you only search over 13 numbers, the pose and shape parameters, which then through that differentiable mapping, like you have this equation, you fit them in, you get out the mesh. Okay? So you can imagine an optimization where you're searching here over all those poses as much as you can, and then things are entered and things are matched. And I'm going to tell you how this matching works. But do you understand what these people did? And they sold the startup. They built that model, right? That essentially tells you how to control that skeleton. And the same thing now exists for hands. The same thing exists for face. The same exists for feet, and so on. Okay. All right. Now here is how we go to do this 2D to 3D. There is an easier problem where you don't need the simple model. And this is called 2D body estimation, which means I give you an image and you spit out heat maps of where the body joints are. And the only thing you need for that is a neural network and lots of annotations. And that's it. This is a standard pixel labeling problem. Like if you have done any pixel labeling, you just need to label different joints. Okay, this is the left shoulder, it's the right shoulder, blah, blah, blah. So but the thing is that because people really care about human body, they've collected insane amount of annotations for this problem. Okay, so you have, and in fact, it also came out of CMU, it's called the Open Pose. It's a software that you can find online that you fit an image or an image of multiple people, and it's going to spit out the 2D poses of all of those. Okay, so how do you go about going from the 2D world to the 3D world? Well, you feed this image and the Open Pose heat maps into a neural network, and the neural network will predict the parameters that control the simple model. Okay, And basically your goal is given an image to predict the parameters that control the simple model. The reason you add this extra input is because they're going to help the neural network. The neural network now knows instead of going from pixels all the way to beta and theta, it goes from pixels and the 2D heat maps into the beta and theta. Okay? Okay. All right. And so the thing is, how do you train that model? Because who's going to give you, like if I give you my picture, do you know the beta and theta of the simple model that renders into my body? Not really. So this is a difficult problem. So how are you going to solve it? Well, the way we solve it is we go in simulation and we render simple there. What do we mean you render simple? You just sample beta and theta, make the mesh, render it through ray casting, and then in this way you get this supervision. You know both the beta and theta and the rotation and translation of the camera. And you can read papers that do exactly this. So basically you can train this from simulation. Let me see if I have this. Yeah, so well, I don't have it. But in any case, in both papers that we see today for imitation from passive videos is all about 3D computer vision. And it's all about going from 2D to those 3D meshes. And as I said, the way we estimate this mapping is we go to simulator and we pre-train it. We pre-train the ways of this neural network. And then we go in the particular video and we self-supervise. What does it mean we self-supervise? We start with some prediction, feed-forward prediction of our network, of beta and theta, rotation and translation. Then we instantiate our mesh, and then we project it back to see how well it matches our input. How do we project it back? Well, we render it back. Now, if this is that's a pretty good guess, by the way. If this is the guy and this is what you guessed, looks good. So what are you going to do? You're going to render back the key point and say, oh, based on my estimation, I think his neck is here. Is it indeed there? And you can do a key point reprojection error. Then you can estimate its segmentation, and you can match it with the bottom-up to the segmentation, okay? Then you can also render its optical flow. So you can take these 300,000 vertices in 2 frames, see their 3D motion, project it down and get the 2D motion, and match it with 2D estimated motion from optical flow. If you want to know more about this, you need to take a computer vision course. They're amazing, such courses in Arai that are, highly recommended. So that's it, basically. This is how this estimation happens. And this actually happens also in our second paper today. You pre-train in simulation and fine-tune self-supervised through the projection errors in the video. And this is just the camera projection. It tells you if you have a mesh and you assume there is a camera, you know precisely which nodes are visible. These other nodes, you are not going to render them, right? That's why you see only the surface of me and you don't see my back. Yeah. So, you don't need to worry about this. And this is what you get. You get per frame 3D meshes if you do what I said. Then you can add some small temporal smoothness, make them a little bit more smooth, and you get that thing, which is not perfect. There is still some jittering. You see the jittering of the leg, but it's good enough to imitate. It's good enough. So now what are you going to do? You'll take that reference motion simply by moving around the joints of that thing, okay? And then you'll try to match that reference motion. So here is the imitation objective. Q hat is the reference motion that is not physically plausible, and you are going to do reinforcement learning to come up with actions of that agent that actually is physically plausible. And essentially, you're just going to do this with PPO, and that's it. But the good thing is that you have dense rewards. All right. So that's precisely the algorithm. Okay. Here is the results. Pretty interesting. There are some failure cases. Here you can adapt it with PPO. RL can adapt the motion to different terrains. Sure. And there are some. So here is a very fast motion. And despite the fact that the reference is not too bad, the simulation, the resulting imitation didn't work out very well. Okay. Maybe because of the high frequency of the moving of the hands. Okay. So we'll stop here. We'll continue on Wednesday. Check the paper because you will learn also some computer vision techniques. And we'll use the same techniques and elaborate upon them for the second paper, which is about imitating in the general world. We're going to see that on Wednesday. Okay. So see you on Wednesday.